Today's video will explain how to optimize decisions when there are two options. Hello, I'm James Helfrich. Decisions are one of the most common things we implement in code, and one of the most common scenarios is when there's two options, option A or option B. It turns out that option A and option B are not equal. This video will explain why that is and how to optimize your code so it runs more effectively in the scenario. There are several different decision configurations. One option, if it's true, I do an action. If it's false, I do nothing. Two options, I do action A or action B. A few options, usually we have if, else if, else if. In this case, I have 4 actions and 3 if statements. And then many options, and usually we use a switch case statement. We're going to talk about 2 option decisions today. Now, in order to understand how this works, we have to understand how a central processing unit, or a CPU, executes instructions. Now, in the beginning, we had, as time passes on, we take one instruction, and when it's finished, we start the second instruction. When it's finished, we start the third. Now, we have to understand that each instruction has several different components. In this case, each instruction has 5 components. Instruction fetch, grab it from memory. Instruction decode, in other words, figure out what it is. Execute, which may take more than one clock cycle. Memory access, and then write back. Now, observe that the CPU is idle most of the time. The fetcher is idle 80% of the time, as is the decoder, and so on. So in the 1990s, we realized we're wasting a lot of CPU time. So let's see if we can organize things differently. And we're going to call this pipelining. So once again, we have the time and the instructions, and then we're going to fetch the first instruction. And as we're decoding the first instruction, we're going to fetch the second instruction. And as we're executing the first instruction and decoding the second instruction, we're then going to fetch the third instruction. And then, of course, as we do the memory access for the first instruction, we're going to execute the second, decode the third, and fetch the fourth, and so on and so on and so on. Now, this looks like it optimizes the CPU really well. All parts of the CPU are active all the time, and this is great, except there's just one problem. Take a look at the highlighted time. When I'm accessing the memory to finish one instruction, then I'm already committed to the next 3. But what if this is a conditional branch operation? What if we don't know if we're going to continue to the next instruction or jump ahead to several other ones? At this point, we don't know. So if it turns out we guess incorrectly, then we got to throw away all the instructions we partially executed and start over. And that's a little expensive. So what the CPU does is it tries to guess which way to go. Now, in the beginning, it always guesses with the true condition. But in modern CPUs, they try to be a little more clever. CPU branch prediction algorithms typically favor the true statement in an if statement. So we're going to put the most likely option first and the least likely option in the else. Now, like we mentioned earlier, some branch prediction algorithms are a little more sophisticated. So it helps if we write some code to measure how our CPU in our language on our operating system actually performs. Now let's take a look at this. First of all, I want to highlight the MS begin and MS end. This is going to get a timestamp of how long it's going to take for this algorithm to execute. The difference between end and begin is how long time transpired. And obviously we want the shortest amount of time possible. Now, notice how Boolean equals option A plus option B and true. Well, this means it's always true, which means we're always going to the true case, okay? As this code currently executes, I'm always going to go into true, and we're going to see how long that takes. Now, if I comment out that line of code and allow for option B, so Boolean equals option A plus option B and false, then we're going to see how long it takes to always go into the else condition. Now, if there is no branch prediction, then option A and option B will be about the same, right? But we're going to assume there's going to be a difference. Now, the third option, the alternate one, Boolean equals option A plus option B and 0, 0, 1 is going to alternate true, false, true, false, true, false. Now, this is going to make it very difficult for the branch prediction algorithm to see what's going on. When I run all 3 of these experiments, I will see how long it takes for option A. In other words, I'm always going the true condition. Option B, always going the false conditions, or the alternate when I go back and forth and back and forth. The prediction is that option A will be the most performant one. Option B will be the second most performant one because any branch prediction will realize I'm always going into false, and the alternate should be the worst, but we can validate this by experiment. Okay, let's run this experiment here. First of all, I'm going to try option A. I'll run option A, it'll take me 18 milliseconds. I'll run option B, and it'll take me 23 milliseconds, so significantly longer. And now I'll do option C, and it'll take 28 milliseconds. So clearly option A is the fastest. You can learn more about this in the 2 options section of the decisions chapter of the software design textbook.